Hello friends. So, we have seen the in our last lecture some of the basic tools that are used for computation of algebraic eigenvalue problem. Large scale algebraic eigenvalue problem, for small scale the definition is good enough, determinant of characteristic polynomial, roots of the characteristic polynomial can give the eigenvalues, but that definition of eigenvalues is not really a sound numerical algorithm when we are dealing with large scale eigenvalue problems. And for large scale eigenvalue problems, we need to look at more efficient data structures and more efficient numerical and stable numerical algorithms. And we saw some of the basic tools of the trade, starting from similarity transform, orthogonal similarity transform. So, they provide us the basic template for developing eigenvalue solvers. By series of orthogonal similarity transform, the matrix can be nudged towards a diagonal matrix or to desired form from which eigenvalues and eigenvectors can be extracted. And suitable matrices, suitable orthogonal transform matrices, they are we saw two examples of that. Givens rotations that will target one element, one off diagonal element at a time, and gradually shift the complete spectral mass towards the diagonal of the matrix. Or second one is of course Householder transformation, where we look at all but the first element of the vector to be annihilated, and that results in n mass zeros enforced on the matrix structure, and that can lead to substantial savings in the computations and leads to very efficient algorithms for eigenvalue solution. So, let us now start with proper algorithms for eigenvalue solution, and we start with our what we started with, the power iterations. So, we discussed all the eigenvectors constitute orthonormal basis, and therefore, any arbitrary vector can be expressed as a linear combination of eigenvectors. So, any trial vector x 0 can be written as a linear combination of eigenvectors, let us say q I. So, q 1 c 1 plus q 2 c 2 plus q 3 c 3 etcetera, and that will be the expansion of x 0, c 1, c 2, c 3, these are the generalized coordinates which need to be determined for a given q for a given x 0, x naught, and for a given set of orthogonal vectors q 1, q 2, q 3 etcetera. So, q I is an eigenvector, a q I is equal to q I lambda I. So, ith eigenpair, and we can define y 0 a vector as a multiplication of a times x 0, and this can be expressed if I represent x 0 as summation of eigenvectors q I c I, then this substitution results in a x 0 is equal to summation of a q I c I, summation over I. And if I take out hypothetical what is the largest eigenvalue, that is common factor, if I take that common factor out, then each of these terms is weighted by this coefficient lambda I by lambda max. So, lambda I is the eigenvalue corresponding to the corresponding eigenvector, ith eigenvector, and lambda max is the largest of lambda i's, all eigenvalues in magnitude. And then we can scale this vector y 0 that we have computed by this factor, let us say y max lambda max, and that gives us new trial vector x 1. And now again I iterate, I use this for multiplication. So, I define y 1, new vector y 1 as a times x 1. So, next cycle begins, and again I take out lambda max as a common factor, and this term now amplifies by 1 power. So, ith term of this expansion is now weighted by lambda I by lambda max squared, and lambda max can be again used to scale and find out what is the next iteration. And after n number of cycles, we will end up with y n, the vector y n will be a times x n, and that will again be equal to, now each term is scaled by a factor lambda I by lambda max raised to the power n. And since each of these terms except for lambda max will be less than unity by definition, because lambda max is numerically maximum value. So, this is this weighting coefficient is always going to be a fractional number. So, raising it to higher power, n is a positive number, and for after sufficiently large number of cycles, n number of cycles, these coefficients will tend to diminish and they will approach 0, and only one term will dominate, and that will be corresponding to lambda max itself, the eigenvector to which lambda max the eigenvalue is the maximum of them, maximum of all eigenvalues, and that vector will dominate, and that is how we converge to the dominant eigenvector. So, the terms with lambda I less than lambda max will gradually diminish in size, and the dominant term corresponding to lambda I is equal to lambda max will only remain in this expansion, in this series. In practice, lambda max is of course not known, and it is commonly done, what is commonly done is vector is scaled to unit length at the end of each iteration, and xi is obtained as scaling of yi such that it has unit length, and that xi is used for subsequent iterations. And the scaling factor that we have here, it converges to the largest eigenvalue, and we can do this exercise, and you can see the convergence happening. So, this second norm is actually the Euclidean norm. So, sum of squares, square root of sum of squares. So, square root of y 1 square plus y 2 square plus y 3 square and so on. So, that is the distance metric in Euclidean geometry. So, entire eigenspectrum can be shifted by introducing a suitable shift parameter. So, for example, I can this is as far as until now we are dealing with the original matrix A, and we find out that no matter what we do, it will end up with the largest eigenvalue and the corresponding eigenvector. So, what to do if we have to find some other eigenvalue? So, that is done by introducing a shift parameter. So, instead of iterating with a matrix A, I consider the matrix as a shifted matrix by a parameter mu. So, I consider the matrix as A minus mu I. So, the entire spectrum is shifted by mu. So, now the eigenvalue for this A minus mu I is lambda minus mu. So, this iteration with A minus mu I will converge to the largest value of lambda minus mu. So, if I can choose mu judiciously, then it is possible to use power iterations for converging to any eigenvalue that we wish. And for that purpose, this shift parameter, Gershgorin radius, the Gershgorin discs, they are very helpful in identifying or choosing the suitable shift parameter, which will allow us to converge to different eigenvalues other than the largest eigenvalue. And of course, if we have computed largest eigenvalue, then mu can be made equal to or very close to the largest eigenvalue, then lambda minus mu. So, lambda max minus mu will be a small number, and then it will be converging to some other eigenvalue. So, for a given mu, the direct power iterations now converge to the eigenvalue lambda, for which lambda minus mu is the maximum. So, in a way it may if mu is close to lambda max, then this A minus mu I might converge to lambda for which lambda actual lambda will be the smallest eigenvalue. And desired eigenvalue lambda can then be extracted from the computed converged eigenvalue lambda star is equal to lambda minus mu of the shifted matrix by undoing the shift operation. So, lambda is equal to lambda star plus mu, and that once we obtain lambda, then we can again go back to A minus lambda I and find suitable corresponding eigenvector corresponding to this eigenvalue, computed eigenvalue. So, now we discussed this the power iterations, direct power iterations, we just matrix multiplication and trial vector and multiplying it by matrix repeatedly and scaling at the end of each cycle, it leads to the largest eigenvalue and the corresponding eigenvector. Now, most of the time what we are interested in is the smallest eigenvalue, not really the largest eigenvalue. Sometimes largest eigenvalue is also required, that we will see in the next topic that we will discuss, the time marching scheme, numerical integration of equations in time. But for most of the analysis purposes, as far as a linear basis is concerned, it is the lower eigenvalue spectrum and lower corresponding eigenvectors that are of more primary interest. And therefore, this procedure of largest eigenvalue converging to largest eigenvalue is little inconvenient, so to say. So, is it possible to look at a procedure by which we can compute the smallest eigenvalue? So, let us look at rearranging this system of equations. So, A x is equal to lambda x, it can also be written as A inverse x is equal to 1 over lambda x, is not it, A inverse. So, I pre-multiply it by A inverse on both sides and then divide by lambda on both sides, and this equation gets transformed to A inverse x is equal to 1 over lambda x. So, that brings us to the basic property of eigenvalues. If lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of inverse of A, and then A inverse x essentially indicates solution of simultaneous equations. So, we do not need to compute A inverse x, we only need to solve the system of equations for x to be as a right hand side vector. So, that is what we do. So, eigenvalues of A and A inverse are inverses of each other, but the corresponding eigenvectors are of course identical. So, power iterations with A inverse, if for some fortuitous reasons we have A inverse matrix available, then power iterations with A inverse will converge to its largest eigenvalue, which, so largest eigenvalue of A inverse, and that would be corresponding to the inverse of the smallest eigenvalue of A. So, if lambda min is the smallest eigenvalue of A, then the largest eigenvalue of A inverse will be 1 over lambda min. So, essentially if I do power iterations with same set of iterations with A inverse, then I converge to the lower end of the eigen spectrum or the lowest eigenvalue and corresponding eigenvector. But as I said, rarely if ever we will have this A inverse with us, and when we say A inverse x, we always refer to it as a solution of simultaneous equation, inverse need not be computed, and we can further try to converge and accelerate the convergence by again using shifted inverse iteration. So, because the convergence actually depends on the ratio lambda I by lambda max. So, if this ratio is made very small, then the convergence is going to be very rapid, and to that effect the shift parameter can be used to great help to converge. And convergence, I mean iterations with A minus mu I inverse iterations, they would converge to the largest value of lambda minus mu, and as I said, explicit matrix inverse is never computed. Instead, the operation A inverse x is implemented as the solution of linear simultaneous equation as A y is equal to x. And once we once we have the root algorithms implemented for solution of simultaneous equations, these equations can be solved repeatedly, and with each iteration, at the end of each iteration they can be scaled and again started with new right hand side vector. So, that is the process for converging to lower eigenvalues or lowest eigenvalue, and rest of the things remain same as a power iteration. Sequentially we compute at each end of each cycle, we scale the vector, computed vector to unit length, and start again with the new vector. So, in case of inverse iteration, we start with the new vector as the new right hand side to be solved for unknowns of equation A y is equal to x, and eventually it will converge to the smallest eigenvalue of matrix A, and inverse of the smallest eigenvalue of matrix A, from which smallest eigenvalue can be calculated, and corresponding eigenvector. So, essentially what we have been able to do so far is calculate largest eigenvalue and calculate smallest eigenvalue by inverse iteration, and if we are lucky and we are more adventurous, then we can play with shift parameters and hope to converge to some of the intermediate eigenvalues. But it is really too much of tedious trial and error work by playing with shift parameters to compute the complete eigenspectrum. There should be a more structured method for arriving at eigenvalues other than the largest and the smallest eigenvalue. And to that we make use of the orthogonality property of eigenvectors. As we said, eigenvectors, they are mutually orthogonal to each other. I mean, we are dealing with a symmetric matrix. If A is symmetric, then the eigenvectors are mutually orthogonal. If A is not symmetric, then left eigenvectors are orthogonal to right eigenvectors. So, there is a bi-orthogonality that exists. So, whichever way we do have some kind of orthogonality available, and that can be used to make the solutions converge to other eigenvalues other than largest and the smallest. Let us see how. So, converging to the other eigenvalues, and this captures the basic essence, explore orthogonal directions. So, earlier we found one direction by power iterations and inverse iteration, we found one direction that gradually converges to the largest dominant eigenvalues, eigenvector corresponding to the dominant eigenvalues. Now, obviously next eigenvector is not going to be in this direction, it will be orthogonal to this. Now, orthogonal can be any way, but that is sure that what has been computed, new eigenvector will not be aligned in this direction. So, that is what we do by a process called vector purification, and we invoke Gram-Schmidt orthogonalization procedure to enforce that the vector trial vector that we use, that is orthogonal to the previously computed eigenvectors. So, if the trial vector that we use for iteration, if that is orthogonal to the previously computed eigenvectors, then of course, it will not, the process will not converge to the previously computed eigenvectors. So, in theory, if we do it once at the start of iteration, that should work, but in practice, because of finite precision arithmetic of floating point operations, there are round of errors, and the orthogonality may be lost during the iteration cycles because of floating point operations. So, this orthogonalization is required at every cycle. So, it is not just a once and then forget. The vector trial vector needs to be made orthogonal with respect to previously computed eigenvectors through the Gram-Schmidt orthogonalization procedure at the beginning of each iteration. So, how do we do this? So, let us consider y 1 and x 1 as left and right eigenvectors associated with the extracted eigenvalue lambda 1, right. So, if lambda 1 is available, then y 1 and x 1. So, left and right eigenvectors can be computed. So, any random vector in n dimensional space can be given as a linear combination of the eigenvectors. So, z as an arbitrary vector can be written as x I c I summation over I. So, x I are the eigenvectors and c I they are the let us consider them, I mean they are generalized coordinates for making up any vector z in terms of x I. Component of z along previously computed eigenvectors can be obtained by using bi-orthogonality property. So, if we have computed let us say y 1 and x 1 are known, then we can compute we can pre-multiply this by y 1. So, y 1 transpose z, and if we look at it, then y 1 would be orthogonal to all eigenvectors except the first eigenvector x 1, and y 1 and x 1 they are of I mean they would be of unit length. So, they can be scaled to have unit I mean such that y 1 transpose x 1 are of unit or unit length that is of unity or whatever number that is. But y I transpose x j where I is not equal to j, that is 0, that is the bi-orthogonality property. So, only one term will remain corresponding to if we choose ith vector y I transpose z, then only ith term in this entire expansion will remain and the rest of the terms will vanish by virtue of orthogonality. So, y I transpose x I that will go in the denominator, and that is what gives us the component to what extent x I is present in making up the vector trial vector z. So, the component of x I in z is c I, and that is given by this relation, the projection. And once we have this, then how do I make the trial vector orthogonal with respect to y I just or orthogonal with respect to x I just subtract the component of x I from z. So, x I is present in z to the extent of c I x I, c I is the weighting coefficient. So, if I subtract c I x I from z, then this component of x I is completely removed and the resulting vector will not have any component along x I, and that is it is orthogonal with respect to x I. So, the purified vector free from the traces of previously computed m eigenvectors is, so if I have computed m number of eigenvectors, then I can compute similar components of all the m eigenvectors and subtract it from this trial vector z. And this new trial vector, purified trial vector, let us call it z hat, and that can be used for iteration. Now, this can be arranged in a matrix form, and I can actually take this, I mean because C I, we have C I here and z is a part of C I. So, this can be z can be taken out and this can be looked at as a matrix. So, I minus sigma I raised to I from 1 to m, and that is a again individual for each ith eigen vector set, we have a matrix that accounts for orthogonality with respect to ith eigenvector. So, this matrix is called sweeping matrix, and when this is multiplied with any vector trial vector, then effectively what it does is it implements this process of computing the component and then subtracting the traces. So, this matrix multiplication will take care of these both operations, computing the component and extent of representation, and then removing the traces of that vector from the original vector, and thereby making it orthogonal. So, this is called the sweeping matrix, and gradually we start with one vector, and then after computing second vector we add one more term to this, and so on. So, we can use this sweeping matrix for gradually improve, and trial iterations can be purified vector can be used by using this sweeping matrix, and at the beginning of each iteration the trial iteration can be again purified by multiplying with sweeping matrix, and then the iterations would converge to eigenvalues largest or smallest depending on whether we are going for forward iteration or inverse iteration, other than this m number of eigenvalues and eigenvectors that have already been computed. So, this is what we call as vector purification, and this can be implemented very easily, although it is not very efficient procedure, numerically efficient procedure. There are more efficient numerical procedures for solving eigenvalue problems, but this is the arguably simplest one to implement on a computer. All that it requires is a series of matrix multiplication, matrix vector multiplication, that is all. So, this can be done very easily and coded very easily, and it can be done for again as a finishing operation. So, these power iterations can be done as a finishing operation for some of the eigenvalues estimates and eigenvectors that are computed from other methods. So, once we have an idea of eigenvalues and eigenvectors, but we need to refine them, then we can use inverse iteration with shift, and that will converge very quickly, and just one or two iterations of inverse iteration with shift parameter, that will produce beautiful and very accurate eigenvalues and eigenvectors. So, another way is to converge to other eigenvalues is not looking at the eigenvector or the trial vector, or removing the traces of computed eigenvectors from the trial vector. Rather, we can modify the matrix itself such that the iterations with the modified matrix do not lead to previously computed eigenvectors. So, we kind of remove the traces of previously computed eigenvectors from the original matrix. So, that is called matrix deflation. So, if lambda 1 and x 1 is an eigenpair of the nth order eigenvalue problem, let us say A x is equal to x lambda, then we consider a Householder matrix P 1 such that P 1 x 1 is equal to alpha times E 1. So, alpha is a coefficient and E 1 is Euclidean unit vector, first Euclidean unit vector 1 0 0 0 0, so on. So, the idea is this reflection matrix P 1 will map x 1 onto the first Euclidean unit vector. So, if I do this, then using similarity transform, we can have P 1 A, P 1 transpose and P 1 x 1, because if you look at it, Householder transforms, Householder transformation matrices, they are orthogonal matrices. So, P transpose P is identity matrix. So, this really does not make any difference. So, P 1 transpose P is essentially identity matrix. So, all that we have done is pre multiply here by P 1 and pre multiply here by P 1. So, P 1 A x is equal to P 1 x lambda, and in between we have this P 1 transpose P, that is essentially identity matrix. So, P 1 A P 1 transpose, this is of course similarity transform, because P 1 and P 1 transpose, they are inverses of each other, and therefore, the eigenvalues do not change, and P 1 x is of course the eigenvalue of this modified matrix, eigenvector of this modified matrix, and lambda 1 is of course the eigenvalue, original eigenvalue. So, what happens? P 1 x is of course alpha E 1, that is unit vector, Euclidean unit vector. So, A 1 E 1. So, if I call this as A 1 and P 1 x 1 is of course unit vector E 1, then this is equal to E 1 lambda 1, and A 1 is of the form P 1 A P 1 transpose, and this is of this form lambda 1, and this is all zeros and these are all zeros, and there is a sub matrix which is A bar, let us call it A bar 1. So, this sub matrix. So, this sub matrix, now if you see, this sub matrix is decoupled from this. So, first eigenvalue is isolated here lambda 1. Now, I can iterate with this remaining sub matrix, and it will lead to, if I do the power iterations, it will lead to the largest eigenvalue, next largest eigenvalue other than lambda 1, if lambda 1 is the largest eigenvalue. If I do the inverse iteration and lambda 1 is the smallest eigenvalue, then inverse iteration will lead to the smallest eigenvalue, which will be smallest for A 1 bar, but larger than A 1 lambda 1. So, submatrix A 1 bar is of the order n minus 1 and can be used to determine eigenvalues other than lambda 1. So, this is used for calculation of the eigenvalues. Once the eigenvalues are obtained, because eigenvalues are identical because of this similarity transform, the eigenvectors, for calculation of eigenvectors, we will of course have to go back to original matrix A. So, eigenvectors should be computed to a very high level of accuracy for implementing matrix deflation, because this reflection matrix P, Householder transformation matrix, that depends on this eigenvector that has been computed earlier. Now, if this eigenvector is in error, then this entire process leads to very poor results. So, the first requirement is of course that the eigenvectors have to be computed to a very high degree of accuracy for implementing this matrix deflation. So, generally this matrix deflation is not used in practice. It is very rarely that you will find matrix deflation being discussed in engineering analysis. Nevertheless, another technique for eigenvalue computation is what we call as Rayleigh quotient iteration. Recall that shifted inverse iteration or shifted direct iteration, they will converge to the largest eigenvalue, and shifted inverse iteration in particular, if I can find an estimate of eigenvalue which is close to an eigenvalue, true eigenvalue, then lambda minus mu, the shift parameter, appears in the denominator. So, if mu is close to lambda, then that parameter becomes very large, 1 over lambda minus mu becomes very large, and that will converge very quickly to that particular eigenvalue close to mu. And to get an estimate of lambda, Rayleigh quotient is a very powerful technique. So, for standard eigenvalue problem, Rayleigh quotient is a ratio of two scalars defined as for any vector x, x transpose A x divided by x transpose x, and for generalized eigenvalue problem it is the ratio of x transpose A x divided by x transpose B x. So, A and B are the coefficient matrices of generalized eigenvalue problem. So, for any trial vector x, this Rayleigh quotient can be calculated, and generally Rayleigh quotient is a good approximation to an eigenvalue, and Rayleigh quotient converges to eigenvalue faster than x converges to the corresponding eigenvector. So, even if x is a very poor approximation to any eigenvector, Rayleigh quotient will in general be a better approximation, or it will be more accurate, higher degree of accuracy. It has a higher degree of accuracy, it is actually second degree accurate, second order accurate to the eigenvalue, true eigenvalue. So, it will converge to eigenvalue, Rayleigh quotient converges to eigenvalue much faster than the trial vector x converges to the eigenvector. So, rho, I mean the Rayleigh quotient is a good approximation for an eigenvalue, and if we have some idea of the shape of eigenvector, then we can just assume that kind of shape, similar shape kind of thing, and compute Rayleigh quotient, and then use this Rayleigh quotient in the inverse iteration algorithm, and this algorithm will converge very quickly to the eigenvalue lambda that is close to rho, that is closest to the Rayleigh quotient rho. So, it can be done for both direct iterations and for standard eigenvalue problem as well as the generalized eigenvalue problem. It only requires different right hand side vectors to be solved for. So, eigenvalue lambda can be recovered from the converged eigenvalue lambda star of inverse iterations on the shifted problem as lambda is equal to 1 over lambda star plus rho. So, that is the Rayleigh quotient iteration, and that converges very quickly, and that is a very handy tool for computing eigenvalues and eigenvectors if we have some idea of the shape of eigenvector that we are looking at. In next lecture, we will discuss more powerful methods for computing a set of eigenvalues and eigenvectors. So far we have been targeting one eigenvalue and associated eigenvector at a time. Now we will look at methods which can give us a large number of simultaneously some eigenvalues and some associated eigenvectors in our next lecture. Thank you.